Hello everyone, welcome to Unravel Logic channel. In today's video, we will be covering variance. This requires you to understand the concept of mean deviation, which is covered in one of my previous videos. So feel free to watch that before you watch this. So let's start. We'll be covering variance. Okay, as usual, let us start with the formal definition. It is the mean of squared deviations. Okay, so variance is mean of squared deviations. I understand that these definitions look kind of scary at times, so this is the reason for this video, right? So let us simplify variance. Okay, we know what deviation means. Okay, so we covered this in one of our previous videos, right? So we covered deviation, right? So we already know what this means, and let me give you a short recap, right? So let us assume that you have a data like this. So let me So this data has a mean of 50, right? This is the mean of this data. Now, when we say the word deviation, we generally mean deviation from the mean. Right? So deviation is nothing but how far that particular point is from the mean. So, for example, we can have 50 minus 10 and then 50 minus 20, 50 minus 30, 50 minus 40, and so on. Yeah, so on, and then so on. Okay, so these are the deviations. Okay, 40, 30, 20, 10 are the deviations of these points from the mean. Okay, basically how much each data point deviates from the mean, as I already mentioned, right? How far each data point is from the mean. Okay, so you can say how far each data point is from the mean. Okay, that is what deviation is. All right, deviation. Now, as per the definition, right, which is mean of squared deviations, so we have the deviations now. When you square these deviations and find their mean, it will be called as variance. Okay, so square deviations and find mean, and you will get variance. Okay, as simple as that. Now naturally the question would be, why would you square the deviations? Okay, so why square the deviations? Okay, what is the reason behind this? Now we'll answer that question now before proceeding further, right? And then we'll cover the examples and intuition and everything. But first let's answer why square the deviations. Okay, let us consider a set of 5 numbers. Okay, so the 5 numbers are 2, 4, 6, 8, and 10. Let's find the mean of these numbers, right? So mean is nothing but sum of all these 5 numbers divide by the total number of numbers, which is 5, right? So 30 by 5, which comes to 6, right? So this is the mean of this set of 5 numbers, right? Now let us find the deviations from the mean. Okay, so let us find deviations from the mean. So we'll have 6 minus 2, 6 minus 4, minus 2, then minus 4. Okay, and if we sum these deviations, we'll simply get let me do it this way. We'll simply get 0. Okay, 0. Yeah. Now why do we get 0? Why 0, right? Because mean is the balancing point of the data, right? Why 0? Because mean is the balancing point of the data, right? So the mean is considered to be the center of the data, right? That is also what it means. Points to either side of the mean are equidistant from the mean, and hence the sum is 0, right? So you can clearly see that this is 0, right? And then this is 2, this is 4, and this is 2 on this side, and this is minus 4 on this side, right? Correct? So if you sum all these numbers, it will be 0, which means that the mean, right, which is this, is the center of this data set. Correct? Now in case of mean deviation, we took the absolute value. Correct? So when we were finding the mean deviation, we took the absolute value, so which is like 4, 2 plus 0 plus 2 plus 4, and then we divided it by a number of numbers, which is 5. So 12 by 5 equals to 2.4, right? This was the mean. And the absolute deviations mean that we neglected the signs, right? So we removed the signs from 2 and 4 and we added those, right? So that is how we find out the mean deviations, right? For variance, we need to square the deviations, right? So what was this? This was mean deviation, correct, of x, right? Let's consider the number as x. Each point in the data set is x, right? Now for variance, we need to square the deviations. Okay, so for variance, square the deviations. So variance of x is equal to 4 square plus 2 square plus 0 square plus 2 square plus 4 square. Okay, and now whether you square minus 2 or minus 4 doesn't really matter. So you can say that we haven't taken the absolute deviations, but we simply took the deviations and we squared them. Okay, and then we need to take the mean of these squared deviations, so that would come out to be 40 by 5, which is equals to 8. So this still doesn't answer your question, right? Why square the deviation? So how did squaring really help, right? Apart from the fact that it gave us a bigger number, which is 8, which is far greater than 2.4, right? So notice numbers 4 and 2 in our data set. Okay, data set 4 is twice as big as 2, right? And if you see, the squared deviations of 4 is 4 times as big as a squared deviation of 2, right? So squared deviation of 4 is 16, right? And squared deviation 2, right, is 4, right? Now again, you see, right, a squared deviation of 4 is 4 times as big as a squared deviation of 2, correct? So So basically this 4 and 2 are deviations, right? But when you square them, right, it's 16 and it's 4. That's what basically I'm trying to say. Okay. Now this tells us that squaring the deviations makes bigger differences even more bigger, right? So squaring makes bigger differences even more bigger. So this is basically saying that it highlights the outliers, right? It goes without saying that it implicitly solves the negative differences problem as well, right? So that we do not have to take the absolute deviation. That problem is solved like implicitly, correct? But other than that, squaring makes bigger differences even more bigger, which means that it highlights the effect of outliers in your data, right? Correct. So that is what it is doing. So if you see this 10, right, and 2 are outliers. So if you see 4, 6 and 8 are kind of close to each other, they each have a difference of 2, but 2 and 10 have a bigger difference, right, from the mean, correct? Now that is what it is highlighting, squared deviations. It highlights the effect of outliers in the data. Okay, so we have understood how squaring helps, right? Now let us understand what does the value of 8 means compared to the value of 2.4, right? Now we squared the deviations, we found out the mean of squared deviations, so we found the variance, but what does it actually mean, right? What does that number mean? So when we are talking about mean deviation, we understood what mean deviation actually means, right, with respect to the data set. But what does variance mean, right? What does 8 means compared to 2.4? So I am referring to this 8 and this 2.4, which 2.4 was the mean deviation, where 8 is the variance. Okay, so what does 8 mean in comparison to 2.4, right? Or what does variance means in comparison to mean deviation? So variance, right? So let's understand the 2.4, the significance of 2.4 on mean deviation first, right? So what we are saying is, on an average, you would find a number 2.4 units away from the mean on the either side of the data. Now if we talk about the variance, so on an if we talk about the variance, what does 8 mean? Degree of dispersion or spread, right? Because we took the deviations, right? So we found out how spread out each point is from the mean, right? And we squared the deviations, found the mean, and we got this number, right? So it can be called as degree of dispersion, degree of spread, right? Which is again the mean deviation is as well, but it gives us a different idea, right? But variance gives us a different idea. So let's understand that by using a real world example. But before that, let us understand the mathematical formula first, okay? So considering the definition, right, which is mean of squared deviations, it is a simple enough formula. Variance of x would be summation from I equal to 1 to n of xi minus x bar is nothing but the mean, okay, and xi minus x bar is nothing but the deviation from the mean, right, and we are squaring it, okay. So if I talk about the elements, right, so this is the observation or the data point itself, okay, ith data point basically, if you consider I equal to 1 to n, okay, and then this is read as x bar, okay, which is also the mean, right, and this n is the number of data points for which we are trying to find the variance. Okay. So this is the mathematical formula, simple enough, right? If you understand the definition, you don't even have to remember this. Yeah. Now let us understand this concept with the help of a real world example, right? So let's cover the example and the mathematical intuition now. Consider the ripening time of tomatoes grown under two different environmental conditions. Ripening time is nothing but the time taken by a fruit to ripen. Okay. So we have two data sets. Okay. So data set 1 is, let's call it D1, tomatoes grown in a controlled environment. Okay. Days to ripen, 68 days, 70, 72, 74, 76. So basically we observed the ripening time of 5 tomatoes. Okay. We have data set 2, tomatoes grown in an open field, basically naturally. Okay. Days to ripen, 60, 65, 72, 79, 84. Now we already calculated the mean and the variance of these data sets, right? Because let's not waste time in calculating the mean and variance, right? Because we know how to do that. We have seen the formula of the variance, right? But what we are trying to understand now is what is the mathematical intuition, right? Where it is necessary, why is it important, right? That is what we are trying to understand. So let's skip the calculation, right? We have already calculated that. So mean of D1 is 72 days, right? So on an average for data set 1, for tomatoes grown in a controlled environment, it takes around 72 days to ripen. Okay. Mean of data set 2 is also 72 days, right? So again, mean doesn't give us much insight into the data, right? So naturally we'll have to use variance, right, to understand any difference in data, right, or what the data is actually trying to tell us, right? So let us see the variance. Okay. Variance of D1 is 8 days square, right? So because we are squaring, right, so the units also gets squared. Okay. Variance of D2 is 77.2 days. So see, right away we can see that there is a lot of difference in variance. Okay, right? Even though the mean is telling us a different story, that everything is same, but variance tells us a lot more, right? Variance is telling us that something is different, right? And it is telling us that there is a lot of difference, right? So two things the variance is telling us, right? Now let us try and find out what that difference is, right? And what that difference means to us, okay? So this simply tells us that the ripening times of tomatoes in dataset 2 vary a lot from the mean or deviate a lot from the mean, okay? So ripening times of tomatoes in dataset 2 vary a lot from the mean or deviate a lot from the mean, right? As we called it, degree of dispersion or degree of spread, right? So it has a high degree of dispersion or high degree of spread, right? So in other words, we can also say that the ripening times of tomatoes grown in the open field are not consistent around the mean, right? So inconsistent ripening times, okay, right? Let us understand why does this make sense and why can we rely on this, okay? So why does it make sense? So if you think about it, right, tomatoes grown in a controlled environment, okay, controlled environment will get the same amount of resources, right? Same amount of resources, right? And in a controlled manner, right? Okay, so they all would ripen almost together around the same time. So the variance or deviations from the mean should be consistent and small, okay? Variance should be small because they all would ripen around the same time, right? And that time would be very close to the mean, right? So the deviations would be small and so the variance would be small, correct? Right? So small deviations, small variance, right? Small, I should say small and consistent deviation. On the other hand, tomatoes, when grown in an open field, okay, open field, okay, would be exposed to different temperatures, weather, sunlight changes and everything, right? So basically different conditions, right? Okay, and we can also say unpredictable, right? Because some area would be exposed to different sunlight, different weather, temperature changes and all those things, right? They happen in wild, right? In open fields, right? So they all would go through different conditions resulting in inconsistent ripening times, right? And so the variance or deviations from the mean would be more for some tomatoes, okay? So variance would be more as deviations for some tomatoes would be more, right? Okay. So low variance tells us about consistency and predictability, okay? Low variance, consistency and predictability, and high variance variability and influence of unpredictable factors in this case, right? So variability, so you can see, right, variance, variability, right, how the words, it's a word play basically. So variability and influence of unpredictable factors or outliers, you can say, right, in technical terms, right? Outliers, there are outliers, yeah. Okay, now next is like when to use. So you can use it to determine the spread of values around the mean, or in other words, to determine the consistency of data around the mean, right? So determine spread of values around the mean, or consistency of data around the mean, right, or even predictability, right? So predictability has a lot more nuances to it, but yeah, I mean, in a very, very simple terms, you can, right, if you want, right, if the data set is not very complex. Yeah, also, I wanted to add another reason, right? So we talked about why square the deviations, right? So I wanted to add another reason that we square the deviations is because the square in the formula helps with the differentiation in advanced statistical concepts. Okay, I wouldn't write this down, but just a note, right? Because there might be some people who are still not convinced, right, that why square the deviations, right? I mean, it doesn't tell us much, but yeah, if you go towards advanced statistical concepts, right, it would help in differentiation, basically minimizing the variance and all those things, right? But we'll come to it at a later point of time, right, when we would have understood more concepts, right, and then it would be easier for you to understand. But yeah, for now, the benefits that I have mentioned hold true, right, for squaring the deviations. Okay, now there are no disadvantages of using variance as such, but it gives us good insights into our data, so it is good to calculate it. Yeah, always calculate, right, variance in your analysis. Okay, because just like in our case, right, the mean ripening time of both the data sets, right, was 72 days, right? So it wasn't giving us much, right? And as soon as we calculated variance, we saw a lot of difference. Yeah, so yeah, do calculate it always, yeah, in your analysis. And thank you for watching. Please like, share and subscribe for more such content.